In this video, we're going to continue our discussion on sequences and talk about a very particular type of sequence called a monotonic sequence. This is going to be a very brief video. We just have a couple definitions, an example, and a theorem. It's not too involved, but we need to know what monotonic sequences are because they can be pretty important. So first, let's just start with a definition of increasing or decreasing sequences. So just a definition. A sequence, AN, is called increasing if AN is less than AN plus 1 for all n greater than or equal to 1. So this just means the sequence is increasing if the terms keep getting bigger. And I'm sure you can guess the definition of a decreasing sequence, but we'll write that down as well. A sequence AN is decreasing if AN is greater than AN plus 1 for all n greater than or equal to 1. So if the terms of the sequence are getting smaller, you have a decreasing sequence. Now we're ready for the definition of a monotonic sequence. A sequence AN is called monotonic if it is either increasing or decreasing. So we're just grouping all of the increasing sequences and all of the decreasing sequences together under one label of monotonic. So if you're told a sequence is monotonic, it could be increasing or it could be decreasing. Now, if you're asked to show that a sequence is increasing or decreasing, there's a lot of different ways to do that. So one option for showing a sequence is increasing or decreasing is you could look at AN minus AN plus 1. So if it's an increasing sequence, then you know that later terms are larger than the earlier terms. So if AN minus AN plus 1 is negative, that means it's increasing. But if it's positive, then it's decreasing. Similarly, you can look at the ratio of AN to AN plus 1. If it's an increasing sequence, then numbers later on are going to be bigger. A number divided by a bigger number is going to be less than 1. So if that ratio is less than 1, it's increasing. But if you get something greater than 1, then it means the numerator is bigger, and you have a decreasing function. Or not function, sequence. So you can look at the ratio of consecutive terms, you can look at the difference of consecutive terms. You could also, if you really wanted to, pull out some of your Calc 1 scales and look at the corresponding function, f of x. And if the derivative of that function is positive, you know, the function is increasing, and so the sequence also is. And if the derivative is negative, your function is decreasing, and so is your sequence. And also you can figure out if it's increasing or decreasing just by using the direct definitions of increasing and decreasing sequences. So let's do one example trying to see if a sequence is increasing or decreasing. So show that the sequence an equals n over n squared plus 1, show that this sequence is decreasing. Well, the definition of a decreasing sequence is that we want an to be greater than an plus 1. So I'm just going to use my sequence and plug in an n plus 1 for the an plus 1 part and see what my inequality would look like. An is n over n squared plus 1. And I want to find out, is this greater than n plus 1 over n plus 1 squared plus 1? And I'm going to go ahead and multiply both sides of the inequality by the denominator of each side. So kind of like cross multiplication. Now you might be a little concerned multiplying an inequality because you know if you multiply by a negative number, we have to flip the inequality sign. But remember what n is. N is talking about an integer starting at 1 when we're listing terms of our sequence. N squared plus 1 and n plus 1 squared plus 1 are both positive. So we don't have to worry about flipping the inequality sign when we multiply by those. So I'm going to have n times my n plus 1 squared plus 1 is greater than my n squared plus 1 times n plus 1. And I want to see for sure if this is true or not. So now I'm going to distribute everything. If I distribute everything on this left side, I have n to the third plus 2n squared plus 2n. And that we're finding out is this greater than n to the third plus n squared plus n plus 1. Well, now let me just move everything except for the 1 over to this left side. So I'm going to subtract n to the third to the left side, subtract an n squared, and subtract an n, and I'll just get n squared plus n greater than 1. All right, so we know that this is true as long, my original inequality is true as long as n squared plus n greater than 1 is true. And this is true. Since n is bigger than or equal to 1. Remember, n was counting the terms of our sequence. So the smallest that n can possibly be is 1. And 1 squared plus 1 is definitely bigger than 1. And as n gets bigger, it's just going to get even more bigger than 1. So this tells me that my entire statement that I've been working with is true, and that means my sequence is decreasing. Now, in order to get to the main point of this video, which is a very important theorem, we need another definition. A sequence is bounded above if there is a number m such that an is less than or equal to m for all n greater than or equal to 1. So this is saying my sequence is called bounded above if there is some number that's bigger than all of the terms of my sequence. And similarly, it is bounded below if there is some other number, little m, such that little m is less than or equal to an for all n bigger than or equal to 1. So it's bounded below if there's some number that's smaller than all of the terms of our sequence. So bounded above, there's something bigger than all of the terms of the sequence. Bounded below, there's something smaller than all of the terms of the sequence. And if your sequence is both bounded above and bounded below, we just call it bounded. So if your sequence an is both bounded above and bounded below, then your sequence an is called a bounded sequence. All right, so now we're about ready for the big theorem of this particular video called the monotonic sequence theorem. But before I can list the monotonic sequence theorem, I have to state a very, very important axiom in mathematics because we need this axiom in order to prove our theorem. This axiom is called the completeness axiom. For the set of real numbers. And this axiom states that if S is a non-empty set of real numbers, that has an upper bound m, then S has a least upper bound. So what this is saying is if you just have a small set of real numbers and you know that they're all less than or equal to some other number, then there is a smallest such number that is bigger than all of the numbers in your set. That would be your least upper bound. It is the smallest thing that can serve as an upper bound for your set. This is a very important axiom that we need in order to prove our very important monotonic sequence theorem. So here is our monotonic sequence theorem. It says every bounded monotonic sequence is convergent. It's a very simple statement, but the proof can be pretty involved. I'm going to prove it for increasing sequences which are bounded above, but we can also prove it very similarly for decreasing sequences that are bounded below. And that's why it works for both of these and why we just have it as bounded monotonic sequences. Now, if we think about this intuitively, it makes sense. If I have a sequence that's increasing, I'm just going to represent that by a bunch of dots that keep getting bigger and bigger and bigger. But there's some value m, which is the upper bound of this increasing sequence, meaning that it's never going to get bigger than that. But I keep increasing, my sequence is going to eventually flatten out and have a convergent limit that's going to converge to that upper bound m. And similarly for decreasing, if I keep decreasing but it's bounded below by something, it's going to flatten out to the thing it's bounded below. So let's have the proof, at least for increasing sequences. So let's suppose that our sequence AN is increasing. Then, since AN is bounded by the assumptions in our theorem says bounded monotonic sequences. So since AN is bounded, we know that the set S, which is the set containing all of the terms of my sequence AN, where n is greater than or equal to 1, has an upper bound. And then it has a least upper bound by that completeness axiom for the real numbers. And I'm going to call that least upper bound n. Then, given any number epsilon greater than 0, we have that m minus epsilon is not an upper bound for S. Now, before I continue this proof, let's think about what this is saying. Since I have a least upper bound, that means anything even just a tiny bit smaller than that least upper bound cannot be an upper bound anymore. Otherwise, I wouldn't have had the least one to begin with. So this is just saying I have a least upper bound m, and anything even just a tiny bit smaller is not an upper bound for my set S anymore. So this tells me then that the terms of my sequence AN have to be greater than m minus epsilon for some value n. So this is just saying I'm going to have some term of my sequence that's going to be larger than capital N minus epsilon, because it's not an upper bound anymore. And then, since my sequence is increasing, we know that AN is greater than or equal to a capital N for all n greater than or equal, all n greater than capital N. Otherwise, it wouldn't be an increasing sequence anymore. So if I have some little n bigger than capital N, then the term of our sequence a little n has to be greater than m minus epsilon. And then that tells me that 0 is less than or equal to m minus an, which is less than epsilon. How I got to that? Well, let me just fill in one tiny little step in between. If I rewrite this as n minus epsilon is less than an, and I'm going to add epsilon to the other side, subtract an from this side, but I know that I have something bigger than 0 because I have an upper bound n here. So I have my upper bound minus the term of my sequence is going to be smushed in between 0 and this positive number epsilon. And then that means we have that the absolute value of m minus the terms of our sequence is going to be less than epsilon whenever n is greater than capital N. And that means that the limit as n goes to infinity of an has to equal n, because I'm getting this n minus an is getting to some arbitrary tiny number epsilon. So the difference between it can be made arbitrarily small, which means that the an have to approach n. And that means that my sequence converges. Now, that was a bit theoretical, and we don't usually go that in depth in proving our things, but I wanted to show you this particular proof because it's a very important theorem. And if I were to do the same thing with decreasing sequences, it's very, very similar to what I just showed for increasing sequences. And the whole point of this is that now that we have this theorem, anytime you have an increasing sequence that's bounded above, you know it converges. And anytime we have a decreasing sequence bounded below, you know that converges as well. So it's sometimes important to be able to tell if a sequence is increasing or decreasing, and then also figure out if it's bounded above or below, because then you can figure out if it converges or not without even necessarily knowing exactly how to take the limit to see what it converges to. So that's about all I have for you on monotonic sequences. Just remember that monotonic sequences are sequences that are increasing or decreasing. And that if your monotonic sequence is bounded, it's going to converge all the time. If you have any questions, feel free to drop them below. If you're a current student, you may also ask in office hours or through email. And I'll see you guys next time.